talking to you. This is Goddess of Science Physics, and I'm Mrs. Bolvin. And today we're going to talk about resonance, which is part 7 of my sound series. Okay, so let's get into this. An object resonates when there's a force to pull it back to its starting position and enough energy to keep it vibrating. Okay, that's really cryptic. Let's see if we can explain that. So if the frequency of a force vibration is equal to the object's natural frequency, the resonance is going to increase the amplitude. If you are causing something to vibrate and the frequency of the force vibration is the same as the frequency, the object's natural frequency, the size of the wave or the size of the vibration is going to increase. You probably have seen this if you've ever had any playground experience on a swing. You pump a swing in rhythm with the swing's natural frequency, you go higher. It makes the amplitude of the pendulum greater. So the timing is more important than the force that you push with. Even little forces at the right time are going to increase the amplitude of the pendulum or of the swing. That makes the arc of the swing bigger. You don't necessarily need a big old underpush. You just need a little force at the right time to get it to do that. So small pushes in rhythm with the natural frequency of the swinging motion will make large amplitudes. When you're pumping a swing, when you're on a swing and you're trying to make it go faster, there's no sense in trying to pump when you get to the edge of or the end of the swing. You want to pump when you start off your swing, your downward swing, so that you get more force there, more energy, and it increases the amplitude. Okay, if you got two tuning forks that are adjusted to the same frequency, hitting one fork will make the other one vibrate. That's just crazy, but absolutely true. Each compression of the sound wave gives the prong a tiny push, and the frequency of the pushes are equal to the natural frequency of the fork. You made it be, if you have two tuning forks that are adjusted to the same frequency, you made them have the same natural frequency. So each of these pushes, even though really tiny, is going to increase the amplitude of the fork's vibration. So even if one of them is vibrating, if there's another one of the same frequency nearby, it can make it vibrate as well. So the pushes occur at the right time and are repeatedly in the same direction as the instantaneous motion of the fork. So here's kind of a cartoony version of what I just said. The first compression gives the fork a tiny push. Okay, so you ding the fork and it makes this one vibrate, and then the fork is going to bend. Kind of looks like that because you've hit it, and it's going to bend a little bit in that direction. Then the fork returns to its initial position, and the vibration goes to this side of the fork, and it keeps moving back and forth, back and forth, back and forth. So it keeps moving and overshoots in the opposite direction. When it returns to its initial position, the next compression arrives to repeat the cycle. So you hit it off this side, it causes this side to bend inward just a tiny bit, but because it's an elastic substance that it's made out of, it will eventually go back, but the compression now has been transferred to this side of the tuning fork, which then will move away a little bit, bend out a little bit, and then it will eventually bend back, and it will send that compression back to the very first side, the initial side of the fork, and that keeps it going back and forth. If the forks are not adjusted for matching frequency, the timing of the pushes will be off and resonance won't occur. So you can't make one if they're not of the same natural frequency, you can't make one fork vibrate another fork. Tuning your radio, and those of you who actually still have radios, is an exercise in adjusting the natural frequency of the electronics in your car radio to one of the incoming signals. So what you're doing is you're changing the natural frequency of the objects, the electronics inside, to match the frequency of one of the radio waves that are coming in. And it could be 104.5, it could be 107.9. You know, you're just changing as you turn the knob on the dial, or in the age of electronics, if you push the button, it will, once you have changed the station, it will come in when the natural frequency of the electronics matches the frequency of the sound wave that's coming in, the radio wave that's coming in. So radio resonance resonates with one station at a time. Sometimes you get like a little bit of overlap there, which is kind of an interesting thing. So there's a couple of different things with Mythbusters there. There's a few videos that you could watch about breaking glass. Interesting case of resonance. It actually did like a huge amount of damage. Whenever you have successive impulse applied to a vibrating object in rhythm, sometimes it can get like out of control. For example, the Tacoma Narrows Bridge collapsed because of resonance. The wind got, it was a suspension bridge, the wind got it vibrating and then just kept the frequency, amplified the amplitude more and more and more, and eventually it actually caused the bridge to collapse over several hours. And it's kind of an interesting thing. The amplitude, because it was constantly being hit with the wind that made it the natural frequency, it made the amplitude greater and greater and greater, and then eventually the bridge couldn't handle it anymore and it collapsed. Nice video there to show you a recording that occurred when the thing collapsed. Okay, well, that's it for this time. Thanks for joining me. Have a great day.